Now let's see how a Python can help us run a z-test by using a function first and then seeing if a library can help us out. So Carly's taught us a lot of math on how to do a z-test, and you've done a lot of z-tests by hand.
Yes.
And while you did a z-test by hand, I was able to write a function that could take a bunch of x values and the expected value of the null hypothesis, the mean under the null hypothesis, and write a function that actually computes it using norm.cdf.
That sounds great.
So I was able to do all of those steps, and I was able to take your math and simply have summing some values, taking the length of the data set, taking some square roots, and doing all of the math that you did. And this is great, and we can always write a function anytime we have a new idea that's brought forward. And we can always just put the math right in Python and let Python do the work for us.
And then we don't have to do it over and over again.
Exactly. And then we've got this function every time we want it. But one thing that as you develop as a data scientist, you're going to want to see, has somebody done the work for you? Can you just use a z-test that already exists? So for this, I would go about and think about just doing a quick Google search and finding if a library already exists. So whenever you're doing a Google search for a programming language construct, you're usually going to want to start your search query with the name of the programming language, because just doing an ordinary z-test isn't going to help us, because we want a z-test that works in Python. So whenever I write a search query, I'm going to say Python space, and then after the space, put whatever I'm looking for. And in general, Google's going to prioritize the first word in your search query as the most important word. So if you say Python first, it's going to say, I definitely want something in Python, and then I'm going to look for everything else. So here, I want to look for Python z-test. And when I do that search query, one of the first results I get is this library from statsmodel.stats.weighted_stats.ztest. So this is going to vary from time to time. So if you do this exact search, you may see a different set of results. I see this as my very first result. And Carly, if you do this right now, I'm just curious, if you search Python z-test in a new tab, do you get the stats models website as the first result on that computer?
Statsmodels.stats.weightstats.ztest. Yes.
Awesome. So this is a library that somebody else has built and published that we can now make use of so that we can do a z-test without having to program it ourselves. So if we look at this, I put the link that I got right here on the handout, so you can click it to go to the exact page, but it tests for a mean based on normal distribution, 1 or 2 samples. In the case of 2 samples, the samples are assumed to be independent. And that's exactly what you said, Carly.
Yep, exactly, for the 2-sample z-test.
So this is going to help us do either a 1-sample or a 2-sample test. And if we look at the parameters, the first parameter we have to give is the x1. So these are the first x values. Second parameter is x2, defaults to none. Value equals 0. So what is this value parameter, Carly?
Ooh, I'm guessing that that's the expected difference.
Yes. So we've always looked at, both 0 as expected difference and looked at some other expected differences.
Yes.
Alternative is 2-sided. So we might have a 2-sided test, or what else could we have?
Oh, so I actually didn't talk about this when I was talking about hypothesis tests, but it's a great point to bring up. So hypothesis tests can either be 1-sided or 2-sided. And basically what that means is that when we're writing our alternative hypothesis, we're either going to specify a direction. We're going to do that our true population mean is less than or greater than some value. And that's what I did in all of my examples. Or sometimes we don't necessarily know which direction it's going to go in. So we could make this a 2-sided test where we basically just say our population mean is not equal to a value, which says it may be lower, it may be higher, it's just not equal to.
So which is the more conservative? Like if we're not sure which to use, which one should we use?
Yeah, the more conservative one is definitely the 2-sided hypothesis. And the thing that's different here is that if we're thinking about our normal curve and our p-value, I've said before it's either the right-hand tail or the left-hand tail. And if we're doing a 2-sided test, it's just both of them. So our p-value is actually doubled for a 2-sided test.
Awesome. So we see that it's defaulting to the more conservative one. So if we just leave it as a default setting, it's not going to give us a bad result.
Right.
We just might have a more accurate result.
Conservative. Yes.
And then we have a number of other parameters. And usually as the parameters get listed, the most important ones are listed first, and then the least important ones are listed later. So let's go ahead and use this Python library. So whenever you see a new library, you have to go ahead and import this library. And the way we're going to do this is every time we see a library name, it's going to have a number of different parts to it. And the generic format of any library is it's going to give in the documentation the fully qualified library name. And that includes the library name all the way from the base library name. So it's going to include a whole bunch of dots. You've seen this in scipy.stats, where we say from scipy.stats import norm. And this is exactly what we're seeing here. We're going to always divide this up by the last dot. So everything to the right of the last dot, this is actually the function name. So the function name is everything on the right-hand side of the last dot, and everything on the left-hand side of the dot is going to be where we can find the function location. So this is the library/function location. So this function location is going to be what we're going to say from the function location, import the function name. So we're going to always use this generic syntax. So from the location, import the function name. So here, the location is stats models, all one word, all lowercase, dot stats, dot weight stats, so not weighted stats, just weight stats. And then we're going to import ztest is the name of the function. So this is going to find the stats model library, and inside the stats model library, find the stats sublibrary and the weighted stats sub or weight stats sublibrary, and then finally import the ztest function. And Carly, if you run this from line to import ztest, you should get no errors.
So I didn't get an error, but I did get a future warning. Pandas.util.testing is deprecated. Use functions in something like that.
So this is a great point. So occasionally when you have libraries that have different versions, you may get warnings when things are going to be changing. So one library developer is using the libraries of another developer. So it sounds like inside of the stats models, it's calling out to pandas. And the version of pandas in the data frame thing has something that's going to go away in the future. But the key word here is you said it was a warning.
It says future warning.
So in computer science, when you have warnings, these are things that aren't going to prevent your program from running, but something you should be aware of. And errors will actually stop your computer from running. So as just a warning, we're going to say, okay, it's fine.
It's okay.
And probably in 6 months, when the stats library or the stats models library gets updated, this future warning may not even exist now. So this is going to be something you may see, you may not see, you may see other warnings depending on what's happening. But as long as it's a warning, we're okay.
Great.
So let's go ahead and use the z-test. But to use the z-test, I want to create some data because this z-test needs data. It doesn't just need statistics. So I'm going to go ahead and let's roll a die. But I'm going to make this dice an unfair dice. So I want to, so Carly, what was your favorite number again?
6.
Your favorite number is 6.
Yes.
So I'm going to create a dice, and I'm going to create a die that actually has 7 sides in Python, and 2 of the sides are labeled 6.
Got it.
So it's going to be an unfair die, and we're going to test whether or not we can test if this die is unfair or not.
Perfect.
So I'm going to go ahead and write a simulation that's going to simulate rolling a die that's an unfair die a total of 100 times. So I'm going to write my classic simulation. So data is equal to square brackets for I in range 100 to run the simulation 100 times. I'm going to say my roll is equal to random.choice. And in my random.choice, I'm going to give a list that contains 1, 2, 3, 4, 5, 6. Then at the end, I'm going to add an extra 6 to the end of my list. So my list has 7 elements in it, 1 through 6 with an extra 6 tagged on at the end. And then I'm going to accumulate this roll inside of my D. So D is equal to curly brace roll in quotes colon roll without quotes in curly brace. Then data.append D, and then df is equal to pd.dataframe of data. So once we've got the simulation, we're using both the random library and the pandas library. So we have to have these 2 additional imports. So we're using 3 imports now just to write a simple program.
And I just went ahead and ran the code, and it looks like it is good.
So if we look at what DF is, I'm going to assume we see 1, 2, 3, 4s, 5, and 6. It's going to look like a pretty standard dice.
That's exactly what I see, 100 rows and 1 column called row.
Called row?
Called roll.
OK, awesome.
Sorry, they sound the same.
Yes. So this is, and it probably looks like a pretty standard dice roll.
Yeah, there's 2 6s at the beginning, but otherwise it looks normal.
So now we can use a z-test to see if we just saw those 100 rolls, we don't know what I've done with this dice. I don't know if this dice is a fair die or not. I'm going to go ahead and use the z-test. So I'm going to find that from the z-test, I am going to use a z-test. And then inside of the z-test, my data is going to be the D at the column roll is going to be my data. So this is my data. And then what do I expect the average of a dice roll to be, Carly?
So the average we would expect to be 3.5.
Yes. So if this was a fair dice, it's equally likely to get every side.
Exactly.
So the first parameter is going to be D at roll. If I scroll up here, what is the name of the value I need to give? I need to say value is equal to 3.5. So value is equal to 3.5. And if I run this z-test, we should see an output.
Oh, did I do this correctly?
DF at roll.
Oops, I typed in D instead of DF.
I actually wrote D, and I just added an F right here.
I guess I was just like being I was
You were
being a
following along
robot.
exactly.
So when I run this, when I fix the DF, it gives me 2 numbers,
Yep.
0.76, comma 0.45.
0.45. So if we look back at the documentation, we want to, and do you still have that tab open?
I do, yes.
So we're going to want to look at the return value section of that website. So if you look down, it's going to give all of the description of all of the parameters, and then it should talk about the return value of the function.
Ooh, it does. It says it returns the t statistic, which is our test statistic, and then the p-value of the test.
So it returns the z-test statistic?
T-test statistic.
Did you get a z-test?
Oh, it says, so no, it says Z. For some reason it says T-stat for test statistic. Sorry.
Sorry, it returns.
T-stat, but that stands for test statistic.
Awesome. So it's t-stat or the test statistic, and this is a z-test. So
Not
this
to be
is a
confused
z-score.
with the t-test.
Yes. So this is where it's kind of, you really have to know your stats.
I
to
really
kind of
had to, I
know.
should have looked at it closer.
So the first parameter is going to be your z-score or your test statistic. And the second parameter is the p-value. So here we have a p-value of 0.45. So Carly, with just 100 rolls, do we have any evidence to suggest that this is an unfair die?
So let's think about this. So the p-value is big, in my opinion. It's definitely bigger than 5%. We know if the p-value is less than 5, we're going to reject the null. But our p-value is bigger than 5. So we're going to say we're not going to reject the null. There's evidence of the null, which was that this was a fair die.
Oh, interesting. So 100 tests weren't enough when we rolled this dice 100 times to figure out whether or not this was an unfair die. We know it was unfair.
Yeah.
But this is an example of why we don't say we accept the null hypothesis either.
Oh, that's a great example.
So this just shows how this can work. And actually, I'm guessing, Carly, you said we can get a better idea of this the more samples we do.
Yes, for sure.
So what if we throw this to 10,000 samples and rerun this?
Should I run it really quick? All right, it ran with no errors. Now let's do our z-test. And now, wow, now our test statistic is 21.1. And our p-value is 1.02 times 10 to the negative 98.
So 97 zeros, then a 1.
Yes.
So with a z-score of 21. So this shows that this is really doing an accurate test, that once we roll this dice 10,000 times, we actually were able to identify this was an unfair die, but only rolling it 100 times, we didn't have enough evidence yet.
That's so cool.
So this is how I love to kind of think of z-test and really discover it and see how it works by using Python. I encourage you to nerd out with Python code just like that, to really intuit the test yourself and understand how it's working and try things out just like this.